Stop, this star existed before the Big Bang. The number on the screen shouldn't exist. 14.46 billion years. That's the age astronomers got for one quiet star drifting in Libra. The problem? The universe by our best clock is only 13.8. Get this, Hubble fixed it. Headlines calmed down, but the math still overlaps the edge. If that number holds, our origin story bends. Did a relic slip through a cosmic reset? Or did we massage a paradox until it behaved? We're going to put this star on trial, its light, its chemistry, its motion, and ask what nobody wants to say out loud. What if time is wrong? Meet the Methuselah problem. So meet the star that started the fight. HD 140,283. Astronomers call it the Methuselah Star. It sits about 190 light-years away in Libra, close in cosmic terms, bright enough for small telescopes, plain enough to ignore if you didn't know its secret. It's a yellow subgiant, moving fast through our neighborhood, and it's almost stripped of metals compared to the Sun. Here's the thing, age isn't printed on a star. You have to infer it. You need distance, brightness, temperature, and chemistry. You plot it against theoretical tracks, isochrons, that say, for a given chemical mix, how stars evolve. The distances, that's parallax. Watch the star wobble against the background as Earth swings around the Sun, then do the geometry. Hipparcos, launched in 1989, made that game precise. Suddenly, for nearby stars, we had clean distances and with them, solid intrinsic brightness. HD 140,283 got its first hard look in that Hipparcos era, and the numbers came back weird. When you took its very low metal content, about 1/250th the Sun's, and laid it on the subgiant branch of those models, the age landed near 16 billion years. People double-checked. They assumed a mistake. A colleague told me later she thought the headline was a hoax until she saw how serious the chatter was at conferences. Why metals matter? In astronomy, metals means anything heavier than helium. The early universe made mostly hydrogen and helium. Everything else came later, forged in stars and thrown back out. So a star with almost no metals likely formed early, out of gas barely touched by previous generations. That makes metal-poor subgiants powerful clocks. As they exhaust core hydrogen and peel off the main sequence, their temperatures and luminosities pass through a tight lane on those isochrons. You get leverage. Small errors in distance or chemistry still leave a narrow age window. But there's a second clock ticking over everything, the age of the universe itself. And that comes from a different path. The cosmic microwave background, the baby picture of the universe, mapped by satellites like WMAP and Planck. Fit a simple model to that pattern, matter, dark energy, and it gives you a precise timeline. 13.8 billion years, give or take a tiny sliver. It's clean. It's anchored by multiple data sets. And now a single nearby star is side-eyeing it. To understand why this wasn't just a quirky outlier, you have to see how the stakes stack. If your universe is 13.8 billion years old, the oldest stars and globular clusters should brush close to that, not blow past it. Stellar chronometers, white dwarf cooling, radioactive dating, and ancient stars. These independent methods all huddle near the same wall. HD 140,283 didn't just touch the paint. It put a hand through the drywall. What nobody knew at the time was where the slack lived. Was the parallax off? Were the bolometric corrections, how you convert what you see through a filter to total energy, biased? Were the model atmospheres missing something about how convection moves energy in such metal-poor gas? Or was the chemistry, especially oxygen and helium, mismeasured by subtle effects in the lines, three-dimensional flows and departures from local thermodynamic equilibrium that skew abundances? Meanwhile, something else was happening across town. Hubble's fine guidance sensor could refine parallaxes even better than Hipparcos for a select set of targets. HD 140,283 made the list. Better distance shrinks the room for error. Its revised age fell from that 16 headline toward 14.5, with stated uncertainties of about 800 million years. Media took victory laps, not older than the universe after all. But wait. 14.46 plus or minus 0.8 still overlaps the edge of 13.8. The seatbelt was the error bar, not a full repair. Here's where it gets interesting. Error bars aren't excuses. They're honesty. They tell you how much room is left for doubt in your inputs and your models, but they also soothe. In a field that prizes concordance, cosmic parameters that agree across methods, tension gets translated into consistent within uncertainties faster than most people read the fine print. Back to the star itself. Its spectrum screams old halo object. Iron deficiency around Phi/H-2, 5 and alpha element enhancement, the kind of oxygen, magnesium, silicon boost you see when early core collapse supernovae set the mix. Its motion through the galaxy looks like a relic from a small system that merged into the Milky Way long ago, an accreted wanderer on a stretched, inclined path. Everything about it says early. So the central question lands and sticks. How can a star that looks this old even flirt with being older than the universe? If the answer is in the star, then our models of metal pore physics, opacity, convection, diffusion, helium fraction, need work. If the answer is in our cosmic clock, then the tidy 13.8 might need slack. And if neither budges enough, well, then we're back at the thought nobody puts on a grant application. To move forward, we have to test the re-aging, not just accept it. What exactly changed when Hubble stepped in? Which assumptions bent to pull the age down? And were those shifts driven by cleaner data or by the need to make everything line up? Everything was about to change when that fix became the story. Inciting incident, the re-aging campaign. 3 days after the Hipparcos era age started making the rounds, a short email thread lit up a small circle of stellar physicists. Hubble's fine guidance sensor could give HD 140,283 a cleaner parallax. It wasn't flashy science, but it was decisive. If the distance was even a few percent off, the inferred luminosity and the age would move. Quietly, the star got on the target list. Over the next several cycles, Hubble stared not for pretty pictures but for micro-arcsecond wiggles. The fine guidance sensor isn't a camera, it's a measuring stick. It tracks guide stars with absurd precision while the main instruments do their work. Repurposed, it can nail down how much a target shifts against background stars as Earth swings around the Sun. For HD 140,283, those numbers mattered more than any dramatic image ever could. When the refined parallax came back, the distance nudged closer. Not a lot, just enough to lower the star's intrinsic brightness a hair. And on the subgent branch, that hair is leverage. Feed the new distance, the observed temperature and the sparse metallicity into modern isochrons, and the peak likelihood slid down. The headline value that hit the press, 14.46 billion years, with a stated uncertainty of plus or minus 0.8. Oldest known, the releases said, but consistent with the age of the universe within errors. Here's where the tone split. In the journals, the abstract language was careful. It emphasized inputs, parallax from Hubble's fine guidance sensor, oxygen abundance ranges, diffusion and mixing in metal pore envelopes, bolometric corrections tuned for this temperature range. It acknowledged systematics, three-dimensional and non-LTE effects on spectral lines, helium fraction assumptions. It even plotted likelihood curves that overlapped the cosmological 13.8 line by tails. On paper, it was a sober update. In the media, a different vibe. Mystery solved. Not older than the universe after all. The plus or minus 8 was doing a lot of work in headlines. If you looked at the figure, the error bars kissed the cosmological wall. If you skimmed the copy, the paradox had evaporated. Get this, several interview quotes framed the new age as reassuring. Concordance restored. Nothing to see here. But wait. Inside the model, several quiet decisions also leaned toward youth. Convection efficiency, the mixing length parameter, was calibrated on the Sun and then ported to a star with 1/250th the metals. Gravitational settling and diffusion of helium and heavy elements were included, which tends to dim and aid a star less for a given position. Oxygen abundance, a key opacity driver in metal-poor stars, was adopted from careful line analyses, but the 3D and non-LTE corrections carried their own spread. Tiny shifts in O/Phi ripple through opacities and ages. None of this is scandalous. It's just the reality. Small knobs matter when your clock is tight. Meanwhile, error bars took center stage. Statistically, they're the seatbelt. They keep you from claiming more than your inputs can support, but they also act like a sedative. Consistent within uncertainties has a way of closing loops that scientifically should probably stay open a bit longer, especially when those uncertainties are dominated by shared assumptions, isochrone families, opacities, mixing prescriptions that show similar biases across codes. Institutionally, there was another pressure. By 2013, Planck's cosmic microwave background analysis was crystallizing the 13.8 number with exquisite precision. Baryon acoustic oscillations and supernova ladders were interlocking into a lambdictum frame that, love it or hate it, fit a lot. A single nearby star that refused to come inside the fence was a poor mascot. Nobody told anyone to fix it. But talk to people in the halls and you'd hear the same instinct. Find the systematics, harmonize the clocks. A micro story from that spring. A postdoc sits at a conference coffee break, laptop open to the HD 140,283 paper. "We finally got it under 15, she says, half relieved, half wary. Her mentor nods. "Good. Now oxygen, we need better 3D grids." He's not wrong, but notice the target. Not let's test the Hubble parallax with Gaia, which was still ramping. Not let's consider whether the cosmological age is flexing. The energy was on making the star behave. To be fair, Gaia would come, and with it, a revolution in parallax that could bless or bruise all of this. High-resolution spectra with full 3D non-LTE modeling would tighten oxygen and helium. Astrocosmology might even whisper about interior structure. Those are the right tests. But in the moment, the re-aging campaign functioned as a narrative patch. A good patch, based on better distance and careful modeling, but a patch nonetheless. What nobody knew at the time was how many other clocks were about to disagree. The Hubble constant would split. JWST would light up two bright galaxies uncomfortably early. Globular cluster ages would keep skirting the wall. So the question hovering over HD 140,283 survived the press cycle. Was this a solved problem or a softened one? To find out, we need to widen the lens and put the universe's clocks side by side. Two clocks fighting, CMB versus supernova versus stars. While that Hubble fix was settling nerves, two bigger clocks were ticking in opposite directions. One comes from the baby picture of the universe itself, the cosmic microwave background. Planck stared at that faint, all-sky glow and read its ripples like sheet music. Those ripples aren't random. They're acoustic peaks from a plasma that rang when the universe was 380,000 years old. Fit a simple model, matter, dark energy, a nearly scale-invariant set of primordial ripples, and you get a timeline. 13.8 billion years, with tight error bars that make statisticians smile. Here's the thing. That number doesn't fall from the sky alone. It locks to a set of parameters that hang together. The matter density that shapes structure, the baryon density that tunes those peaks, and the Hubble constant that tells you today's expansion rate. Planck's combination pulls h down, about 67 kilometers per second per megaparsec, and that slower rate naturally stretches the age. Slower today means older total time. The CMB clock likes a roomy universe. 13.8 to the first decimal, neat and tidy. Meanwhile, across town, people were building a ladder. Type Ia supernovae, white dwarfs that blow at a consistent peak brightness, let you measure distances to far-off galaxies. You calibrate them with nearby Cepheids, pulsating stars whose period brightness link is bulletproof, then step outward. Do that carefully and you can read H directly, here and now. Teams did it. They got numbers around 73 or 74. Higher H means the universe is expanding faster today. Push that logic back through the equations and, for the same matter content, You shave time off the age. That's how you end up closer to 13 billion years than 13.8. So we've got a split. The early universe says slow today, older total. The local universe says fast today, younger total. Both methods tighten their uncertainties. Both check systematics to the bone. Dust in host galaxies, metallicity of Cepheids, 0 points set by parallax calibrations, supernova light curve training, lensing of the CMB, foregrounds, beam systematics, map-making pipelines. The tension refused to die. If you're keeping score, that's a billion years swinging on which clock you trust. Now drop in the stellar chronometers. Subgiants like HD 140,283 are sharp because their position off the main sequence pins down how long core hydrogen burning lasted. Globular clusters bring crowds, ancient metal-poor populations whose turnoff points press against the same wall. White dwarf cooling sequences tick like embers fading in a hearth, their slope telling you how long they've been cooling since the last stars in a cluster formed. And radioactive dating, thorium and uranium lines in ultra-metal-poor stars, lets you run a nuclear clock, though with caveats about initial production ratios. These aren't as precise as Planck, but they rhyme. Old, 13 plus, often brushing the edge the CMB drew. Why subgiants matter in this fight is leverage. Their ages don't care about the Hubble constant directly. They care about distance, chemistry, and physics inside a star. So when a subgiant says 14 point something with conservative assumptions, it isn't taking sides in the H-war. It's handing the referee another stopwatch. Same with the oldest globular clusters that land between 12.5 and 13.5 billion years, depending on which isochrons and distances you choose. They crowd the fence Planck erected. And then there's the crisis frame that nobody wanted to say out loud until people started saying it out loud. It wasn't just one mismatch. It was many, nibbling at the same story from different angles. The H-split. Early galaxies that looked too beefy too soon in JWST's first deep fields. Stellar clocks that, when pushed by conservative physics, didn't give you the slack you wanted. Each one survivable alone. Together, they made the room feel small. Get this, precision is the villain and the hero here. As measurements sharpen, the slack vanishes. Consistent within uncertainties gets harder to say with a straight face. A 5% error bar lets everyone be friends. A 1% error bar forces choices. Either there's a shared systematic nobody has cracked, some sneaky calibration fault linking Cepheids to supernovae, or an unmodeled foreground in Planck's maps, or the universe is telling us the 6-parameter lambdictum paint job needs a touch-up, not a bulldozer. A touch-up that changes which clock we trust in which regime. Meanwhile, the human angle keeps this from becoming a dry catalog. Picture a room in Santa Barbara in 2019. Teams lay out their numbers. People who have argued for years sit 6 feet apart, nodding as plots land. Someone jokes about the name, problem, discrepancy, crisis. Laughter, then a quiet. Because if the clocks don't agree, it's not just an equation. It's our origin story. Did we build a model so clean we forgot to leave room for what's messy? Or did we tune the story around the cleanest clock and shove the others into error bars? Here's where it gets interesting. The CMB clock is global and early. The supernova ladder is local and late. The stellar clocks are personal, stars aging in place. If there's a fix, it has to respect that geography. New physics that tweaks early times could ease Planck without wrecking late growth, or late time twists in dark energy could reconcile H without wrecking the acoustic peaks. Or the answer sits in the stars, opacity tables, convection recipes, helium fractions, waiting for asterosismology and Gaia's final parallax word. Stakes stay high because the timeline slack is shrinking as precision climbs. And the Methuselah Star, it's not the judge, it's a witness. Its testimony doesn't end the trial. It forces us to keep both clocks on the wall, ticking loudly enough that we can't ignore the beat. Inside the star, metal-poor physics and model risk. So now we open the star and look at the gears. HD 140,283 isn't just old, it's strange in a way that matters for age math. Its iron abundance sits around Phi/H-2, 5, which means about 1/250th the Sun's iron content. It's also alpha-enhanced, oxygen, magnesium, silicon boosted relative to iron, the signature of early core collapse supernovae. That chemistry changes how light moves through the star. And in stars, how light moves decides how fast the clock runs. Start with opacity. In metal-poor gas, there are fewer lines for photons to grab onto, so radiation leaks more easily. Lower opacity means energy escapes faster, which changes the temperature gradient in the envelope. That, in turn, shifts the star's surface temperature and luminosity for a given core state. On an isochrone chart, a small change in opacity can move you along the subgiant branch, the way one extra click on a safe dial can pass the right number. You can land older or younger with the same parallax, just by adjusting the microphysics. Then there's convection. We use a knob called the mixing length parameter to describe how efficiently convective blobs carry heat. It's tuned on the sun because that's where we have the best constraints. But get this, porting a solar-calibrated knob to a star with almost no metals isn't guaranteed to be right. Some recent work, the Meredith-Joyce-style revisions, explored what happens if convection is less efficient in stars like this. Suppress it a bit, and the star's surface gets cooler at the same evolutionary stage. On a plot, that nudges the inferred age down without changing the distance. Small knob, big swing. Diffusion, the slow sinking of helium and heavy elements under gravity, matters too. Over billions of years, elements settle out of the outer layers, changing the surface composition we measure compared to the interior. Include diffusion and the star can look a hair different for the same total age. Exclude it and you bias ages the other way. The fix isn't to pick a side. It's to model both diffusion and some counteracting mixing, then carry the uncertainty honestly into the age. Now oxygen. In a metal-poor star, oxygen's a heavyweight because it contributes a lot to opacity even when iron is scarce. But measuring oxygen at these temperatures is hard. Different spectral lines tell different stories. The forbidden OI line at 630 A ring is clean but faint. The triplet around 777 A ring is strong but sensitive to non-LTE effects, departures from the simple assumption that atoms are in local thermodynamic equilibrium. Add 3D hydrodynamics, granulation, waves, updrafts, and the line strength shift again. A 1-2 dex change in O/phi ripples straight into the models. Raise oxygen and you tweak opacities, shift the track, and with it, the age by hundreds of millions of years. Helium fraction is a ghost in this room. We don't measure helium directly in a cool subgiant atmosphere. We infer it from chemical evolution models and consistency with Big Bang nucleosynthesis. Change the initial helium a little, and the core burns differently. Ages respond. It's not a free knob. CMB and primordial abundances fence it in. But the residual freedom is enough to matter at the 1 gigayear level we're sweating over. There's also the mixing length's cousin, overshoot and envelope mixing. How far does convection reach beyond its formal boundary? How much does turbulent mixing blur the neat zones our equations draw? Metal-poor structures can be more compact. Their convective boundaries might not mirror solar behavior. Overshoot changes core mass at hydrogen exhaustion, and that cascades into subgiant luminosity at a given age. If you're feeling like the ground is moving, that's the point. Isochrone families, Yale, Yonsei, Dartmouth, BASTI, bake in choices for opacities, nuclear rates, mixing length, diffusion, and boundary conditions. They agree in broad strokes, but their scatter at low metallicity is not 0. Pick one grid and you get 13.7. Pick another with a different oxygen adoption and you get 14.4. None are cheating. They're carrying different, defensible assumptions into an edge case where leverage is brutal. Meanwhile, two stubborn puzzles echo in the background. Lithium is low in old metal-poor dwarfs, the famous spite plateau sitting below standard Big Bang predictions. In subgiants like HD 140,283, surface lithium is also depleted by mixing. It doesn't age the star, but it reminds you our treatment of light elements and mixing is still evolving. And oxygen remains a two-front fight. Better 3D NLTE corrections on the lines, and better propagation of that uncertainty into the age. Halo kinematics add a human note. HD 140,283's elongated, inclined orbit looks like an accreted relic from a dwarf galaxy, formed early, tossed into the Milky Way later. If it's a fossil, its physics should scream primitive conditions. That pushes modelers to ask a hard question. Did we tune our recipes to match sun-like stars and clusters, then trust them too much out here in the thin air of Phi/H, -2.5? Or did we nudge them, consciously or not, toward cosmological comfort? What nobody knew at the time was how much these micro-decisions would dominate the star's headline age once Hubble removed most of the distance slack. Parallax moved the dot onto the right street. Opacity, oxygen, helium, and convection picked the house number. If we tune those dials to make it fit, we'll see it when truly independent measures arrive. Gaia's final parallax, high-ray spectra with full 3D NLTE oxygen, asteroseismology to feel the interior. Until then, the risk is clear. Small model choices can shave 1 billion years off a star that might actually be chewing gum at the edge of the universe's timeline. The chemical forensics. To figure out where this star was born, we have to read its ashes. That means chemistry, line by line. HD 140,283 wears a classic population II signature. Almost no iron, boosted alpha elements like oxygen and magnesium, and nothing fancy past barium worth bragging about. It looks like it formed from gas touched by a handful of early core collapse supernovae, not a rich stew of later explosions. Oxygen is the loudest witness. In metal-poor stars, oxygen dominates opacity, so its abundance matters more than iron for age tracks. But oxygen is slippery to measure. You can chase the faint forbidden OI 630 A-ring line, which is clean but weak. Or you can use the strong OI triplet around 777 A-ring, which pops but lies to you unless you correct for non-LTE effects. Add 3D hydrodynamics, granulation, convection, waves, and both sets shift. 1/10 of a dex either way and the isochrons walk. Ages do with them. Analysts run both routes. They build 3D NLT models to correct those lines, then compare. The best work lands around an oxygen to iron ratio that screams early enrichment. Big alpha bump, small iron seed. That's consistent with a clock that started fast. Massive stars lived, died, and seeded the gas within tens of millions of years. It's also what you'd expect if this star grew up in a small, hungry dwarf galaxy, where a few explosions set the mix, and then the party ended. Lithium whispers a different truth. In the very oldest, hottest dwarfs, there's a famous plateau in lithium abundance that sits well below Big Bang predictions. Subgiants like HD 140,283. Their surfaces have already mixed and diluted lithium, so the number you see isn't primordial. Still, the pattern matters. Low lithium at the surface, with a history that matches depletion tracks, says mixing and diffusion have been at work for billions of years. It doesn't prove an age, but it supports the idea that surface chemistry isn't the same as the interiors. That feeds back into models and error bars. Heavy elements help too. In some ancient halo stars, uranium and thorium lines let you run a nuclear clock. HD 140,283 doesn't give generous uranium, but the general pattern, weak S process, modest R process, fits a world before low-mass asymptotic giant branch stars had time to pollute the gas. Early times, quick cycles, few enrichers. Again, the vibe is primitive. Now what chemistry can't do is license wild claims. There's no known pathway that drops a fully formed star across a Big Bang boundary. Conformal cyclic cosmology talks about information and radiation gliding from one eon to the next, not intact suns with fused cores crossing over. So if you're hoping for a spectral feature stamped previous universe, this isn't it. The forensics narrow birth conditions. They don't break cosmology by themselves. But chemistry can point to birthplace. HD 140,283's alpha pattern and iron poverty, paired with its halo-like, elongated orbit, look like an accreted relic. Picture a tiny dwarf galaxy forming its first stars from nearly pristine gas, then getting torn up by the young Milky Way. One survivor slings into our neighborhood on a stretched path. That explains the low metals, the fast motion, and the early clock without magic. There's one more wrinkle. Oxygen uncertainties bleed straight into the age. Even with 3D and LTE work, different teams get slightly different O/Phi. And helium, the ghost we can't measure directly here, rides along. Adopt a modest helium fraction consistent with Big Bang nucleosynthesis and the CMB, and the models settle. Push it and ages budge. That's why the best papers show likelihood bands, not a single point. So where does the trail leave us? The spectrum says early generation, likely in a small system with alpha-rich chemistry that tightens the clock. The oxygen spread still buys or sells hundreds of millions of years. Lithium reminds us mixing is real. None of it proves older than the universe. But none of it lets you wave the paradox away, either. If this isn't a glitch, it's a fossil from the first sparks after the lights came on. And if that's true, then the next question is, from before the Big Bang, it's sharper. Did we quietly tune the physics to make this fossil fit our favorite timeline? Or will independent tests lock its age where the numbers still sting? The pre-Big Bang theory's on trial. So if the chemistry can't smuggle a finished star across the Big Bang, why did older than the universe stick around? Because the timeline felt tight, and when timelines feel tight, people start testing the walls. Enter the pre-Big Bang ideas. Not YouTube sci-fi, serious attempts to answer a real question. What, if anything, came before the hot beginning we can actually see? Here's the first stop. Conformal Cyclic Cosmology, CCC for short. Roger Penrose's pitch is wild but precise. Take our universe in the far future when expansion has run so long that matter has decayed, black holes have evaporated, and what's left is essentially radiation, massless stuff. In that limit, the world forgets about scales. Big and small don't mean much when everything moves at light speed. Penrose uses that trick, conformal geometry, to glue that stretched-out future boundary to a new Big Bang surface. No crunch, no bounce. Just a handoff of geometry from one eon to the next. What in that picture survives the crossing? Not planets, not stars, not atoms. Information in a sense. Radiation patterns and ultra-energetic events whose imprint can carry through the conformal map. Penrose and collaborators even claimed a specific signature, Hawking points, hot spots in the cosmic microwave background where giant black holes in a previous eon dumped their final radiation. They've published analyses saying those circles exist. Other groups ran the same tests and said, we don't see it. It's not settled. But either way, CCC doesn't predict intact suns cruising across eons. It's about patterns in the earliest light, not fossils with cores. Now bounce ideas. The ekpyrotic model says our hot Big Bang was a collision, brains in higher dimensions brushing and igniting a new cycle. The matter bounce flips the script. The universe contracts slowly in a way that smooths and flattens things, then bounces into expansion, seeding the same kind of nearly scale invariant ripples inflation gives you. These models fight to solve the same headaches inflation was built for: horizon, flatness, structure, without a hair trigger in flattened field. They live or die by predictions. Non-Gaussian features in the CMB, primordial gravitational waves, or the lack of them, spectral tilts, isocurvature modes. Again, none of them say a pre-bang star shows up after the bounce with its isochronal birth certificate intact. There's also the simple cyclic vibe. Expand, contract, repeat. Those versions wrestle with entropy. If disorder grows each cycle, how do you get a fresh low entropy start again? Some proposals dump entropy into extra dimensions or spread it out so each cycle resets clean enough to look like ours. Elegant on a chalkboard, hard to square with every observation we've got. So what evidence would count for any of these? For CCC, robust, blind detections of those Hawking-like points across multiple CMB maps with agreed-upon significance. For ekpyrotic or matter bounces, clean non-Gaussian patterns and a suppressed primordial gravitational wave background compared to the inflationary expectation. For any cyclic model, a crisp, testable feature, say, a step in the primordial power spectrum, that shows up in both the CMB and large-scale structure. Notice what's missing: a metal-poor subgiant down the street. HD 140,283 just isn't the kind of evidence these theories talk about. Get this, HD 140,283 as a relic from before would require new physics no current pre-Bang theory provides. You'd need a mechanism that carries bound states, heavy elements, and nuclear burning history across a conformal or dynamical boundary while keeping the rest of cosmology recognizable. That's not on the table. Penrose's own writings are explicit. What crosses are conformally natural things, like the traces of radiation from evaporating black holes, not baryonic structures. But there's a reason the star gets dragged into these conversations. It's a symbol. When your best cosmic clock says 13.8 and your sharpest fossil flirts with 14+, it tempts you to throw rocks at the origin story. It's fine, healthy, even to keep those rocks handy. The crisis frame we opened earlier isn't a conspiracy, it's a checklist. If the early time model needs help, pre-Big Bang options get a seat, the same way dark energy did when supernovae said accelerating. Here's the integrity check though. You don't let a metaphor drive the bus. HD 140,283 can pressure models of stellar physics, parallax, and chemical corrections. It can't single-handedly validate CCC or bounce cosmologies. The bar for those is sky-wide and multi-channel. CMB maps, polarization, lensing, baryon acoustic oscillations, primordial abundances, and yes, JWST's early galaxy demographics. Past those, then we'll talk about bending beginnings. Meanwhile, what nobody knew at the time, older than the universe, first made the rounds was how sticky that phrase would be. It hung around because it's catchy, because it needles our sense of order, and because, frankly, institutions like being tidy. If a pre-Big Bang theory were going to win here, it wouldn't be on a single star. It would be because the whole tapestry, early light, structure, growth, lab physics, pulled the same way. So we test the big ideas on their turf. We test the star on ours. And we keep one promise to the audience and to ourselves. No theory gets a free pass because it has a poetic answer to a headline. Up next, we tighten the screws on the age ledger itself. Distances, reddening, nuclear rates. The quiet knobs that decide whether HD 140,283 is a headline or a harbinger. Rising tension, the age ledger and its loopholes. While everyone argued theory, the age ledger came down to quiet numbers that could slide under your feet. Start with distance. Hipparcos gave us the first clean parallax for HD 140,283, but it wasn't the last word. Hubble's fine guidance sensor tightened it, and then Gaia arrived promising micro-arcsecond truth. Early Gaia releases were a gift and a warning, stunning precision with small systematics lurking, color-dependent biases, zero-point offsets, crowded field quirks. For a subgiant this bright and nearby, those shifts are tiny, but age on the subgiant branch is hypersensitive. Nudge the parallax, the luminosity jumps and the age rides along. Reddening is next. You'd think dust wouldn't matter much for a star 190 light-years away in a clean halo path, but even a hair of extinction, misestimated by, say, 0.01 magnitudes, changes the bolometric correction and the inferred temperature. That folds into the luminosity, and now you're moving along the isochrons again. Bolometric corrections themselves are model-made, tuned by atmosphere grids that assume certain opacities and line lists. Update those lists, and yesterday's correction is today's bias. Distance modulus math sounds dull, but this is where headlines live. Add parallax p with a 0.z, invert to distance, fold in reddening EB minus V, apply a bolometric correction BC that depends on temperature and metallicity, then land on absolute magnitude. Each term has an error bar. Alone they're fine, together they stack. And when the story you're telling hangs on a billion-year swing, compound uncertainty beats narrative certainty every time. Isochrone families add another layer. Yale, Yonsei, Dartmouth, BASTI, they don't just change fonts. They embed different opacity tables, surface boundary conditions, mixing lengths, diffusion treatments. Plot the same star with phi/h approximately -2, 5 and alpha/phi approximately +4 across those grids, and you'll see subtle spreads in the subgiant track. Not chaos, but enough scatter to matter. Pick one family because it matches clusters, and you've quietly imported that family's habits into a star sitting right at the leverage point. Now the nuclear knobs. The CNO cycle barely runs in such a metal-poor star compared to the proton chain, but oxygen still drives opacity. And nuclear reaction rates, the S-factors you pull from labs and theory, carry uncertainties that ripple into core temperatures and luminosities at turnoff. Opacity tables themselves. Opal versus op, metal mixtures, updated line blanketing, shift radiative transport. You won't swing 5 gigayears with a new rate, but a few 100 million years. Absolutely on the table. Meanwhile, systematics don't announce themselves. A 0 point in Gaia parallax can be spatially varying. A bolometric correction grid can be calibrated on metal-rich dwarfs, then stretched into metal-poor subgiants where molecular bands and continuum edges behave differently. Spectroscopic temperatures can ride on 1D LTE fits that 3D NLTE work later softens. Each adjustment is small and defensible. Together, they decide whether your abstract says 13.7 or 14.5, with consistent within uncertainties, tagged on the end. Here's the stakes line. Small tweaks decide cosmology-sized headlines. If parallax, reddening, bolometric corrections, and isochrons nudge in the same direction by chance, or by community habit, you get concordance that feels earned but rests on correlated assumptions. Flip one sign, and the star starts tapping the cosmological wall again. A micro-story from a data room. A grad student cross-matches HD 140,283's Gaia parallax with a catalog that corrects the global 0 point using quasars. She frowns. Her correction shifts the distance by a fraction of a percent. Her advisor shrugs. That's in the noise. She runs the full age pipeline anyway. The posterior mean ticks up by 100 million years. Not a crisis. But add an updated oxygen NLTE correction and a refined BC grid, and the combined move is 3 times that. The plot in her talk looks the same. The number in the corner feels different. So how do you defend against quiet drift? You cross-check clocks that don't share the same knobs. Globular cluster ages rely on turn-off points and distances tied to eclipsing binaries and RR Lyrae. Their white dwarf cooling sequences measure a separate slope. The temperature, luminosity fade that clocks time since star formation stopped. Nucleosynthesis in ultra-metal-poor stars uses uranium and thorium decay as a nuclear timer. Messy, yes, but independent. When those land near 12, 513, 5 billion years with realistic spreads, you see a pattern, near the edge but not beyond it. Concordance or collision. Right now, it's more like crowding the same fence. Oldest clusters brush 13+. White dwarf sequences backstop that. U/TH ages with big caveats about initial ratios, don't scream younger. None of them rescue a star that truly wanted to be 15. None of them slam the door on 14 either, if your inputs all lean old. And that's the tension. Precision has squeezed the slack. The ledger is cleaner, but the loopholes are human-sized. Calibrations, corrections, shared priors. If we want this star to stop being a Rorschach test, we need parallax that locks, reddening that's pinned, bolometric scales benchmarked on metal-poor standards, and isochrone intercomparisons run blind. Until then, every small choice is a vote. Enough votes one way and the timeline looks safe. enough the other and the edge feels sharp again. Cross-checks, globulars, uranium, thorium, white dwarfs. While the ledger's knobs kept sliding, another question mattered more. Are there independent clocks that don't share those knobs? If HD 140,283 is telling the truth, the oldest crowds in the galaxy should echo it. So we go where time piles up, globular clusters. Picture M4 through a modest scope, dense as spilled salt. In that swarm, stars were born together from the same gas, then aged in lockstep. That's a gift. You can read a cluster's age from the turnoff, the point where the main sequence peels away as stars run out of core hydrogen. Turnoff brightness plus distance gives you the number. Distances used to be the weak link. Now we've got eclipsing binaries setting absolute yardsticks, RR Lyrae with period, luminosity ties, and Gaia tightening the scale. Run the fits and you get a pattern. The oldest clusters brush 12.5 to 13.5 billion years, depending on which isochrone family and metallicity you adopt. They crowd the fence plank drew, near, not through. A micro story. A team works on NGC 6397, one of the closest globulars. They measure an eclipsing binary, nail the distance, and refit the turnoff. The age drops by a few 100 million years from the last decade's number. Someone cheers, someone sighs. It's still old. It still presses the wall, just not the wall's wrong side. Turn the clock another way down into the embers. White dwarfs are stellar cores stripped of their envelopes. No fusion left, just hot cinders cooling into the dark. Their cooling is physics you can love. Well-understood heat capacity, crystallization kinks, neutrino losses early on, then a slow fade. In a cluster, plot the white dwarf luminosity function. How many at each brightness, and you get a slope and a cutoff. That cutoff is a timestamp. Star formation stopped at least this long ago. For M4 for 47 Tuck, for NGC 6397, those cuts land with ages that backstop the turnoff numbers. You don't need the same convection knobs. You don't need oxygen lines. You need distances and good photometry, and you get an independent old. Again, near 12.5 to 13 plus, near the fence. Now pull out the most audacious timer in the drawer. Radioactive decay inside ancient, ultra-metal-poor stars. In a few rare cases, you can see thorium and even uranium absorption lines in a halo star spectrum. Thorium-232 and uranium-238 decay over billions of years. If you know their initial production ratios from our process nucleosynthesis, you can compare then to now and get an age since the elements were forged. It's messy. Initial ratios depend on poorly known astrophysical sites, maybe neutron star mergers, maybe jet-driven supernovae, but it's a different physics base. Famous examples like CS30-1080-2001 and HE15-233901 return ages around 13 billion years, with uncertainties of 1 to 2. Not clean enough to split hairs, but loud enough to stay ancient. Here's the pattern that keeps showing up when you put them side by side. Globular cluster turnoffs, white dwarf cooling sequences, and nucleocosmochronology don't form a chorus that shouts older than the universe. They hum a chord at the edge. They agree there's not much slack. They sit close to 13, sometimes into the low 14s if distances and isochrons push old, sometimes down a few 100 million years if new calibrations nudge young. The center of mass of all these clocks is conservative, near the wall, not beyond it. So where does that leave Methuselah's testimony? Two things at once can be true. One, independent clocks validate that our oldest stellar populations live right up against the 13.8 window. Two, none of them run fairly, demand a breach. That's not a sedative, it's a constraint. If HD 140,283 wants to land at 14.4 with tight errors, then parallax, oxygen, helium, and mixing had better be nailed by data we don't have yet. If it slides to 13.7 when Gaia Doctor 4 and 3D NLTE oxygen settle, then the fence feels earned. Meanwhile, the crisis frame doesn't evaporate. The clocks crowd the edge while other tensions, Hubble split, early luminous galaxies poke from different angles. Concordance is holding, but you can hear the beams creak. Which brings us back to the wider crunch. When multiple anomalies stack, do we patch, or do we listen for the model asking to grow? The cosmology crunch. H. Early galaxies and edge cases. While the stellar clocks crowded the fence, the big crunch came from two directions that shouldn't both be right. The first is the Hubble tension. Planck's early universe fit says H is about 67 kilometers per second per megaparsec. The local distance ladder, parallax to Cepheids to type Ia supernovae, lands around 73 or 74. That's not a rounding error. It's a canyon that refuses to close as teams sharpen their work. Here's the thing. If H is really 73 plus, the age you back out in a flat lambdictum world tilts younger by a few 100 million years. Faster today generally means less total time since the hot beginning. That shaves the cosmic slack we've been leaning on. If H is 67, the age stretches, and the 13.8 looks more comfortable against ancient clusters and subgiants. One number, two ages. Pick your poison right. People didn't pick. They audited. Latter teams hammered dust laws in host galaxies, metallicity in Cepheid calibrators, crowding corrections in HST fields, and 0 points from Milky Way parallaxes. They even pulled in megamasers, water maser orbits that give geometric distances to a few special galaxies, because nothing says trust like Kepler's laws in another galaxy. Meanwhile, CMB folks beat on beams, foregrounds, calibration transfer, and lensing reconstruction. Add baryon acoustic oscillations from galaxies surveys as a cross brace. The split held. And while that argument simmered, JWST opened a new front. Its first deep fields lit up with candidates at redshifts 10, 12, even beyond, galaxies as they were a few 100 million years after the Big Bang. Some looked bright and massive, with star formation rates that implied brisk assembly. Headlines wrote themselves, "Too big, too soon." Timelines started to feel tight in a new way. But wait, photometry at the edge is slippery. A handful of filters and a strong emission line can trick you into thinking a galaxy is farther and beefier than it is. Dust can redden a nearer object to look distant. Gravitational lensing can magnify a background source, making rare beasts look common if you miss the lens. Teams chased spectra, clean breaks at Lyman alpha real redshifts. Some objects slid down, others held. Masses ticked downward with better modeling, but a few stayed punchy. The early sky still looked busier than our most cautious priors guessed. Here's where modelers started sweating. If even a fraction of those early heavyweights are real star formation in dense, metal-poor halos ran hotter than our recipes assumed. Make pristine gas cool efficiently, let massive stars form early, and you can front-load light without breaking anything. Black hole seeds might appear sooner, accrete faster, or grow by direct collapse in rare pockets. Feedback that chokes star formation later might not bite as hard in the first few 100 million years. Subgrid physics, our compression tricks, needed new terms. Meanwhile, surface brightness dimming is brutal. Flux per area drops as 1 plus Z4. JWST sensitivity helped, but selection still favors the bright end. We might be seeing the luminous tail because that's what we can see. That's not a bug, it's a bias. As spectroscopic follow-up improves and lensing maps sharpen, some of that too big attention is cooling. Not gone, cooled. The room is still tight. Stack the tensions. H-split narrows the age window if the local number wins. Early luminous candidates tug the growth curve earlier. Stellar clocks crowd the fence. Globulars and white dwarfs don't rescue you with extra slack. It's not one anomaly. It's a pile, each small alone, pointed the same way together. So is lambdictum broken, not so fast. The core scaffolding, flat geometry, cold dark matter, a cosmological constant, still nails the CMB's acoustic peaks, baryon acoustic oscillations, lensing maps, and primordial abundances. You don't bulldoze a house that's anchored at 20 points. You look for where a beam is bending. There are levers. Early dark energy, a brief injection of energy density before recombination, can tweak the sound horizon the CMB measures. lifting H without wrecking the peaks. It's narrow, has to turn on and off at the right time, and current data already fences it in hard. Interacting dark radiation or extra-effective neutrino species can shift early expansion subtly. Late-time dark energy that evolves away from a pure cosmological constant could bend distances enough to ease the latter without gutting structure growth. Every option pays a price somewhere. That's good. It keeps us honest. On the observational side, more cross-checks are loading. Strong lens time delays measure H without Cepheids or the CMB. Tip of the red giant branch distances bypass Cepheid systematics. Megamacers add clean anchors. Intensity mapping and deeper bow surveys will refine the distance scale. JWST will turn more candidates into confirmed high-Z galaxies with spectra. Each new constraint either loosens the knot or tightens it until something snaps. And the edge cases, voids, cold spots, odd morphologies, stay in the room as tests, not trump cards. A rare supervoid might add a micro-Kelvin dip to the CMB. An unusual galaxy size might be lensing in disguise. Under-rendered, number under-modeled until data forces a better model. So here's the stakes line plain. As precision climbs, the universe is giving us fewer places to hide. If H stays split, if early galaxies keep crowding the dawn, if stellar clocks keep tapping the same wall, then lambdictum needs an add-on. Not a rewrite, an amendment that shifts just enough in the right era to reconcile honest clocks. If the splits fade under better data, we win clarity. If they don't, we win new physics. Either way, the Methuselah Star forced us to listen for creaks we might have tuned out. Motives and methods. Is science patching or progressing? So is this progress, or are we quietly papering over cracks? Here's the thing, science isn't a straight march. It's more like a tightrope with safety nets, peer review, shared priors, cross-checks, and yes, error bars. Those nets keep you from declaring victory on noise. They also nudge you toward consensus. Concordance feels good. It reads well. That's a motive you have to name if you want to trust the outcome. Start with peer review. Reviewers ask, did you use established isochrons? Did you account for 3D NLTE and oxygen? Did you fold diffusion and mixing? Those aren't box-sticking games. They're guardrails so a single choice doesn't swing an age by a gigayear without warning. But wait, what counts as established bakes priors into the cake? If all the major codes converge because they share opacity tables, mixing prescriptions and solar calibrations, then independent can hide correlated bias. Review protects against sloppiness, not against the habits of a field. Error bars live in that same tension. Best case, they're honest budgets that say, here, S what we don't know, here, S how much it can move the answer. Worst case, they're a sedative. Consistent within uncertainties becomes a reflex, especially when the headline on the other side is "Star older than the universe." Institutions don't conspire. They prefer coherence. That preference shows up in which uncertainties get airtime and which get parked in appendices. Press releases widen the gap. A careful paper says 14.46 plus or minus 0.8, model dependent, oxygen systematics dominate. The headline becomes, mystery solved, not older than the universe. The motive isn't sinister, it's narrative gravity. You can see the comfort, a tidy lambdictum age, a dramatic star brought to heel. But the method, the real work, lives in tables, likelihoods, and model intercomparisons most people never read. Here's a micro story. A young researcher submits a paper that pushes HD 140,283 older by 300 million years using updated oxygen corrections and a slightly different mixing length. Reviewer 1 says, solid, compared to JWST and Dartmouth. Reviewer 2 says, why not adopt the solar calibrated alpha, concordance matters? The author compromises. Main text uses the field's default, appendix shows the shift. The paper passes. The press picks the default. Did the institution patch the paradox or just choose stability over an edge case? Both truths fit. Now healthy skepticism versus conspiracy. It's easy to read re-aging campaign and hear cover-up. That's not what the record shows. The Hubble parallax was a legitimate upgrade. The modeling choices are in the open. The community is arguing in public about age, early galaxies, non-LTE, Gaia 0 points. Conferences in Santa Barbara, policy notes on blinding analyses, independent pipelines for Planck maps. This isn't a cabal. It's a herd that likes to move together until the data yanks it sideways. Case study time. Methuselah's age walkdown was model-driven. Distance got cleaner, then microphysics carried the swing: oxygen, helium, convection, diffusion. Each knob had a citation trail. Each shift was plausible. The total drift felt purposeful because the destination, 13.8, was sitting there like a lighthouse. But the method didn't falsify alternatives. It weighted them down with priors. That's patching in the best sense. You add layers until the leak slows. Progress is when an external test rips the patch off or fuses it into structure. So what counts as progress here? Falsification that bites. If lambdictum is to be bent, the bend must be forced by multiple blind, cross-checked measurements, not one star's age PDF. Clear criteria, not vibes. For cosmology, move H with strong lens time delays and tip of the red giant branch distances that agree, then show early dark energy fixes the CMB and bow without wrecking structure growth. For the star, lock the parallax with Gaia Dr. 4, Dr. 5 systematics nailed. Measure oxygen with full 3D NLTE grids agreed across teams. Constrain helium indirectly with asterosismology or population synthesis. And then carry those into isochrone families in a blinded intercomparison. And for the motives, build process that resists comfort. Blind analyses where the cosmological age line is hidden when stellar ages are fit. Isochrone bake-offs where teams run the same inputs through different codes without seeing each other's outputs until the end. Press offices that quote the largest credible interval, not the prettiest point estimate. Reviewers who ask authors to show how each prior moves the posterior. Small cultural shifts, big trust payoffs. Here's where it gets interesting. If we do that and Methuselah still wants to sit at 14 points something with tight shared systematics, then the patch peels. We'll owe the timeline room, either in stellar physics we swore was settled, or in early universe parameters that Planck seemed to freeze. If instead, the star settles at 13.7 when the oxygen dust clears, that's progress too. The paradox pushed us to clean every hinge. So is science patching or progressing? Both, by design. Patches keep the ship afloat while we map leaks. Progress is when a weld replaces the tape. Methuselah forced both instincts into the open, which is exactly how a field earns its story. The tests that settle it. So what actually settles this? No more patches, no more vibes. First, distance. Gaia Dr. 3 sharpened the map, but Dr. 4 and Dr. 5 are where the 0 points get nailed. Quasars pin the global offset, color and magnitude terms get cleaned, and bright star systematics, right where HD 140,283 lives come down. One parallax, one uncertainty you can't wiggle with rhetoric. If that shifts the star's luminosity even a hair, the age moves with it. That's step one, lock the yardstick. Next, spectra that don't lie to us about oxygen and helium. We need deep, high-resolution observations from instruments that can feed full 3D/non-LTE analyses. Think VLT Espresso, Keck HIRES, Subaru/HDS, on both the Forbidden OI line and the 777 NM triplet, plus OH lines in the UV where possible. Run them through 3D hydrodynamic grids that model granulation and flows, not toy atmospheres. Publish line-by-line abundances with shared priors and show how a tenth of a dex in O/Phi moves the age. On helium, we won't see it directly in a cool subgeant, but we can fence it with population synthesis, primordial constraints, and maybe, just maybe, asterosismic hints. Which brings us to asterosismology. Subgeants ring softly. TESS and Plato won't turn this star into a symphony, but even a small set of P-mode frequencies, or a clear large frequency separation, tells you the mean density and carves down model degeneracies. Pair that with the parallax and temperature, and you've pinned mass and radius tightly enough to expose whether convection, diffusion, or opacity assumptions are doing heavy lifting. If the interior structure says younger track, it'll show. If not, the old age holds its ground. Then we remove code culture from the result. A blinded multi-code isochrone bake-off. JWST, Dartmouth, MIST, YSI, JWST. Same inputs, same abundances, same bolometric corrections. Run without seeing each other's outputs, then unblind. Plot the age posteriors on the same axes. If they cluster, great, we've got robustness. If they scatter, we know where to push opacities, mixing length calibration, boundary conditions, until convergence is real, not social. Dust and bolometric scales get their own audit. Even tiny reddening matters, so use 3D dust maps and local probes to bound E, B-V, to the millimagnitude. Recalibrate bolometric corrections for metal-poor subgiants with benchmark stars, nearby halo subgiants with interferometric radii and flux-calibrated spectra. Tie the temperature scale to those, not just to solar analogs stretched into the metal-poor regime. Every 0.1% here pays out in hundreds of millions of years there. Cross fields tighten the vise. If H stays high from strong lens time delays and tip of the red giant branch distances, the cosmological age shrinks. The star must then live on the younger side of its allowed band. If Planck's fit flexes with early dark energy in a way that passes bow and lensing, the room widens. A 14-ish star hurts less. Either way, the test is external. Don't move the star to fix age. Don't move H to fix the star. Let both be measured and see who blinks. Globulars and white dwarfs serve as sanity mirrors. Refit the oldest clusters with the same blinded isochrone suite, Gaia-anchored distances, and new bolometric scales. Check whether their turnoffs and white dwarf cooling cutoffs crowd the same fence the star does. If independent clocks all tick in step, trust goes up. If one sings off key, find the systematic there, not here. And communication matters. Pre-register the analysis plan. Blind the cosmological line on plots during the stellar age fits. Publish likelihoods, not just pretty points. Quote the full credible intervals. Show the sensitivity to each prior and make every dataset open. What nobody wants to admit is that this is winnable either way. If Gaia, oxygen, helium, and seismology converge on 13, 6, 13, 9, the paradox dissolves and we learn a lot about metal-poor physics. If they converge on 14 plus with tight, multi-code agreement, then cosmology owes us slack, early time tweaks that respect the rest of the sky. Both outcomes are progress. The only way we lose is if we stop tightening the bolts because consistent within uncertainties feels good. So we run the tests, we keep them blind, and we let the numbers land where they land. If the timeline bends. So what changes if this timeline really bends, if the oldest clocks refuse to step back? Two clean paths. Scenario A, everything tightens and lines up. Gaia nails the parallax, 3D NLTE oxygen lands narrow, asterosismology fences the mass, and HD 140,283 settles in the 13, 6, 13, 9 pocket. The Big Bang's 13.8 breathes easy. We still win because we learned where age slack hides. In convection recipes, oxygen opacities, bolometric scales. The paradox did its job. It forced precision and exposed where we'd been hand-waving. Scenario B. The mismatch persists. The distance holds, oxygen stays high, models converge across codes, and the posterior pins old. Not cartoon old, just old enough that the cosmological fence feels too tight. Then early time physics has to flex. Maybe a short burst of early dark energy trims the sound horizon and lifts H without breaking the CMB peaks. Maybe extra dark radiation rewrites the pre-recombination expansion by a hair. Maybe the matter power spectrum wants a slight tilt tweak. None of that is wrecking balls. They're controlled edits where the model can actually take weight. Culturally, this is the part that matters. You stop treating single numbers like commandments, you trust methods. If the clocks crowd the edge, you don't panic. You test what can actually move. A field grows up when it can say, our favorite answer might shift and keep the rest of the scaffolding standing. Copernicus didn't erase the sky. He relabeled it. Same here. A tweak to early energy density or light relics doesn't burn lambdictum. It patches the seam where new data tugged. Here's the thing most headlines miss. Anomalies aren't errors to erase. They're engines. The reason we have a precise origin clock at all is because people chased tensions that once looked like nuisances. Missing mass in galaxies, supernovae too faint, a microwave whisper nobody expected. Every one of those was a crisis until it was. If Methuselah keeps tapping the wall, it joins that lineage. If it quiets under better inputs, that's a result too. The engine still ran and tuned the machine. On the human side, this is also self-defense against whiplash. The next time you see universe broken, ask 3 questions. Is the effect confirmed by independent teams? Do the methods share systematics? Is there a clear prediction that could fail next year? If you can't answer yes to at least 2, save your neck. If you can, lean in. The best stories earn their drama by risking the next test. Personal lens. This whole chase started because a plain yellow subgiant down the block forced people to sit through boring talks about parallax 0 points and oxygen triplets. That's the work, not the meme. A billion-year swing sounds huge until you watch how it comes down to 1/10 of a dex in O/phi, or a millimagnitude of dust. Get this, meaning hides in those small numbers because that's where a field proves it can be wrong without breaking. So if the timeline bends, the meaning is we were lied to. It's we learned how to listen. You don't need a pre-Big Bang star to have a bigger universe. You need the willingness to let a fossil ask a rude question and to answer it without moving the goalposts. Either we walk away with a star that taught us stellar physics under extreme poverty, or we walk away with early time physics that got 1 degree richer. Both futures are wins. Now hold that promise we made at the top. We detest the star, the math, and the motives. We did. The only thing left is to decide what to do with that feeling in your gut, the one that says keep watching the edge. That single subgiant forced us to put every clock on the table and listen for creaks we'd been tuning out. If the edge holds or flexes, the lesson is the same. Truth rides in methods, not headlines. If you want the next move, how early dark energy could shrink the sound horizon without wrecking the peaks, cue up our deep dive here. Subscribe for more honest, uncomfortable checks on reality and share this with a friend who only reads the headline. Then tell me below, patched model or bent timeline, which way are you betting?